Hi class, we're now in 17.5, the autoionization of water and looking at a pH scale. So an autoionization of water, we've discussed this prior, is amphoteric, which means it can act as an acid or a base. When water acts with itself as an acid and a base to form ions, this process is called autoionization. So all aqueous solutions contain both hydronium ions and hydroxide ions. The concentration of hydronium ions and hydroxide ions are equal in water. So if we take a look at this here, we have acid and a base, and HCl is a strong acid, so it completely ionizes. The water will take the proton and it produces hydronium ions and chloride ions. Now water acting as an acid will donate its proton, producing hydroxide ions, and the proton will go with ammonia, producing ammonium ions. Now water acting with itself, one will act as an acid, one will act as a base, we will produce hydronium ions and hydroxide ions. So they are equal to each other. So not only can water, again, this is just repeating, can act as a proton donor and an acceptor, it also reacts in the same reaction. So you can see with water, one is a hydronium, one is hydroxide. This is autoionization, where it proceeds to a tiny extent because water is a weak acid and it's also a weak base. So the product of the hydronium ion and hydroxide ion concentrations is always the same number. This is called the ion product of water, and it's known as the Kw. It's also known as the dissociation constant of water. So when we set this up, remember the brackets, so this is the concentration of hydronium ions, and the concentration of hydroxide ions is equal to Kw, and Kw is equal to 1.00 times 10 to the negative 14 at 25 degrees Celsius. If you measure one of the concentrations, you can figure out what the other one is by using this, setting it up to this constant. So since this is a constant, that means that these are, one will go up, the other one must go down. So they're inversely proportional. So here's an example. Let's take a look at this. So Kw is temperature dependent, as all equilibrium constants are. So if we look at Kw is 0.68 times 10 to the negative 14 at 10 degrees Celsius, 1.0 times 10 to the negative 14 at 25 degrees Celsius, and 5.48 times 10 to the negative 14 at 50 degrees Celsius. So in pure water at 25 degrees, we can, if these are equal concentrations, we can set it up as x squared and make it equal to 1.0 times 10 to the negative 14. If we use the square root to reduce the square, then we end up with 1.0 times 10 to the negative 7, and those concentrations are equal for both. Okay, so the Kw equilibrium is always in effect in aqueous solutions. And because it's a constant, that means that the concentration of hydronium ions and hydroxide ions are inversely proportional, meaning if one increases, then the other one has to decrease by an equal factor. Okay, so neutral solutions have equal concentrations of 1.00 times 10 to the negative 7, because this will still equal, both of these will equal 1.00 times 10 to the negative 14. If it's an acidic solution, that means it has a larger concentration of hydronium ions, which means it will be a larger number than this. Now remember, when I say larger number, it means this number here is lower, because that means less zeros in front. So it's kind of deceiving when you say larger, but you're dealing with smaller zeros. If the hydroxide ion, and that means the hydroxide ion will be less than this number. So this might seem confusing, so focus on one right now. Basic solutions have a larger hydroxide ion concentration, so that means that this will have a larger value, which means smaller numbers than this value. So let's take a look at this again. So I just said if you have a larger concentration of hydronium ions versus hydroxide ions, it's an acidic solution. If we have a larger concentration of hydroxide solutions versus hydronium ions, it is a basic, and if they are equal, then it is a neutral. So adding acids to water increases the hydroxide ion concentration. Adding bases to water increases the hydroxide ion concentration. And in both cases, the system must shift to reestablish the equilibrium. So let's put this into understanding this more. The hydronium concentration of 3 solutions at room temperature are as followed. Which solution is acidic? So if we look here, remember, I'm saying larger values, which means smaller numbers makes them more acidic. The larger the number makes them, in this case, more basic. So in this case, we would pick A because it's less zeros in front, which actually makes it a larger value. So that is what's happening here. So if you get confused, write these out with the zeros and you will easily see which one is the correct one. Okay, so water ionization, we can set this up as an equilibrium. You can see that we can produce the X. This is where the X square comes from because they're equal concentrations and they will be equal to this KW value. All right, but that has now, remember that I told you that the KW is equal to 1.00 times 10 negative 14. We can use that to determine the concentration of the other concentration that's not available to us. So in this case, it's asking for the hydroxide concentration. So we can set this up using the KW value to determine the hydroxide ion concentration. So with the first one, we can solve it with the KW. So we set it up. We plug in the value that we have, which is the hydronium, and we solve for the one we don't, which gives us 7.7 times 10 to the negative 11. Now we need to know if this is acidic, basic, or neutral. So remember, it all has to equal this. So if one goes up, one must go down. So this is a larger value. So this is an acidic solution. There's less zeros here than here. And if we look at the second one, we have the hydroxide concentration again. We plug this in, and this gives us 1.3 times 10 to the negative 6 compared to 7.9 times 10 to the negative 9. This is a smaller value. So this, but remember, we're looking at hydroxide solution, not hydronium. So this solution is basic. It has more concentration of hydroxide ions than hydronium ions. So the pH scale, dealing with these large numbers for molarity makes it kind of hard to remember which is which. So this is where the pH scale, remember when I talked about the pKa, it's a lot easier than dealing with Ka. This is the same thing in a sense. Learning the pH scale makes it easier to understand than dealing with long scientific notation numbers all the time and remembering what the inverse of the one has to be. So the pH scale is more, it's very convenient because if you understand the number range, then you will instantly understand what solution you're dealing with. Where this, my mind's blank. You have to think about these numbers. Okay, so let's go over a pH scale. pH values range from 1 to 14. Technically, they start at 0, and are typically, if the pH is less than 7, it is acidic. If it is equal to 7, it is neutral. And if the pH is more than 7, it is basic. Now, the pH has to do with the hydronium concentration. How much hydronium concentration exists? So remember, all these reactions, weak and strong, they all produce a hydronium concentration. How much is a different story. But this is what we're looking at, is that hydronium concentration. So how do we get from what to what? So if we want to know the pH, we need to know, I even highlighted this or blocked it. We need to know the hydronium concentration to find the pH. You have to know, in order to do the pH stands for the hydronium concentration, so we need to know that. We use the negative log of the concentration of hydronium ions. You plug this in, it will give you the pH. Now, if pH is less than 7, it's acidic. So 0 to 6.9 is considered acidic. 7 is neutral. And let's say 7.1 and on is starting to go basic to 14. Now, what if you had the pH though, but you need the hydronium concentration? Well, you simply you plug in this right here on your calculator. Make sure you have a negative. This is the one thing that students forget. If you do not put the negative, you're going to get a way different concentration of hydronium than you need. So remember this negative here, negative pH to the 10, which I'm sorry, I still can't remember what this is called. I probably could look it up in the book. But you understand that this is on your calculator. You can plug in the negative pH and it will give you the hydronium concentration. Then you can also figure out with the plug-in if you needed to know the hydroxide concentration, for instance. So if you had this to start with, you could get this, plug this in, it could determine this. So here is some pHs so you can see. We start here at gastric juices. They range from 1 to 3. Limes, lemons, soft drinks. How's that for your teeth? Then we go to wines, apples, peaches, cherries, beer. Beer is acidic. Rainwater is actually rather acidic, even if it's unpolluted. Ocean water is, I believe it's pH 8.2, so it's basic. Human blood is between 7.3 and 7.4. Egg whites, milk and magnesia. This makes sense because if you know what milk and magnesia is, it's an antacid that helps curb stomach acid. So when you get heartburn or an upset stomach, it's a base to help neutralize excess stomach acid. Household ammonia, and 4% sodium hydroxide solution is 14. Okay, so this is a very important slide. You definitely need to make notes on this because this is where people mess up, and they mess up big on something that is not that big of a deal if you could just learn it once or write the rule and make sure you enforce it. So, sig figs. The lower the pH, the more acidic the solution. The higher the pH, the more basic the solution, which means less hydronium concentration. 1 pH unit corresponds to a factor of 10 in difference. So it's very different from a pH 3 to a pH 4. It's a huge difference. pH 0 is a hydronium concentration of 1 molar. pH 14 is a hydroxide concentration of 1 molar. So the bigger the number is for hydroxide concentration, the stronger it is. And the opposite for hydronium concentration, the lower it is, the stronger the concentration. pH can be negative and larger than 14, but we really don't deal with that. Now, this is the part I'm talking about. If you have a log number where you plug in your hydronium concentration or even hydroxide concentration, the sig figs are going to determine your pH value. So, and it's not what you think it is. The value of the sci-fi notation number here is 2 sig figs. So when you have to put a pH, you ignore the first number and your sig figs are added after the decimal point. So you should always have one more value than what you have here. So in this case, if I have 2, I should have 3. And vice versa. I take 2 sig figs here. I need to make sure I have 2 sig figs here. This is simple but difficult at the same time. So this is a slide you definitely should pay attention to. pOH is the concentration of hydroxide ions. So if we want to know the pOH, we take the concentration, the negative log concentration of hydroxide ions. And then if we had the pOH, we could determine the hydroxide concentration. So it's the same, but we're looking at pOH, not pH. And again, we need to know the hydroxide concentration to find the pOH. So what is the pOH? Well, the pH plus the pOH equals 14 on the pH scale. So make sure that you're dealing with pH. If you're dealing with pH, and make sure to keep note if you're dealing with pOH, they are not the same. And if you plug in the concentration of hydroxide ions trying to get the pH, it's going to be wrong. So I have an example of that. Okay. So relationships between pH and pOH. So I can find the pOH by determining the hydroxide concentration again, using the water constant. The ion product of water or the dissociation constant of water. Plugging this in, this is simply showing you where this comes from. So this is the water, the constant. You can plug that in because that's representative of this. Take the negative log of it and it gives you a pOH plus pH 14. So if you have the pH, you can subtract it and you can determine what the pOH is and vice versa. So as the pH of a solution increases, what happens to the acidity of the solution? So remember I said anything below 7 is acidic. So as you get closer to 0, it's a stronger acid. If you go in the other direction towards 14, it's more basic. So the acidity decreases. So as the pH increases, it's going to decrease because you're starting to get into the basic range of, let's say, 7.1 to 14. You want the number to be as low as possible if you want a strong acid. So determine the pH of each of the following solutions and classify each as acidic, basic, or neutral. This is a very good slide to learn how to do these problems. So we have 1.0 times 10 negative 5 HCl. So what is the pH of that? So we would use that calculation of the negative log of the concentration of hydronium ions, and we would plug that in. Now let's look at the sig figs. So it would give us a pH of 5, but we have 2 sig figs here. So either remember that whatever you have here plus 1, which means 3, or you have 2 sig figs, you start at the decimal point, and you have 2 sig figs, and this is acidic. Now we have 0.100 molar of nitric acid. We plug that in. It gives us a pH of 1.00, and this is one that I don't understand where this one came with the 2 sig figs here, and it's got, I'll be honest, I can't figure out why this has 2 sig figs, but it's got 3 sig figs here, and it's acidic. So this one's throwing me off. I can't tell you. I'm not sure. Okay, now this one's longer because we're dealing with the base. We're dealing with hydroxide concentration, not hydronium concentration. So in order to do a pH, we need to find out the hydronium concentration. So in this case, we first need to use the kW to determine the hydronium concentration. So this is 2 steps. Once we get that, we can plug that in, and then we can determine the pH. And the pH is 12.90. This is 2 sig figs after the decimal point. So this is basic. So sig figs in pH calculations, only the digits that come after the decimal point in the pH value are significant. So a pH of 6.23 has 2 sig figs, not 3. So this is a good example of how you can easily make a mistake. The number of sig fig digits in the concentration determines the number of digits after the decimal point. So, oh yeah, look at here. This is yeah, that other one I think is wrong. Because you see, this has 3 sig figs. So it should have 3 sig figs after the decimal point and not 2. And that one should have 3 sig figs. This should have another 0. No wonder why it doesn't look right to me. See, caught it. This should have another 0 to match 3 sig figs that are here, which is exactly what it's saying here. There's 3 sig figs, so this should have 3 sig figs after, not 2. Glad we figured that out. The hydronium concentration can be determined by taking the inverse log, that's what this is, inverse log of the negative pH. I don't know why I can't remember that. So what do? You take the pH, remember it's negative. This isn't easy, I've done it many times. That's why I'm saying this. If you don't put the negative sign, you are not going to get the right answer at all. So if you put this, then you can get the correct hydronium concentration. Now here's a little easy kind of shortcut. If you have an exact integer, then that is what the hydronium concentration is. See the number here? Plug that number in. See the number here? Plug that number in, and that tells you what it is. Now in this case, this is 1 sig fig, so that's where you see 1. This is 2, and that equals 2. All right, so determine the hydronium concentration. This, by the way, is a longer lecture because I have a lot of examples. Determine the hydronium concentration for a solution but using the pH values, and we're going to determine whether it's acidic, basic, or neutral. So we have a pH 10. So again, we use the inverse log. I got to write that down. So here we take the inverse log, the negative, let's see if I can say this correctly, the inverse log of the negative pH. So this is the inverse log of the negative pH. Plug that in, make sure it's negative, or you're not going to get the right number. And that gives you 1 times 10 to the negative 10 molar. This is a basic solution. And I mean, you can just tell by the 10 here. This is acidic because it's lower than 7, but we still need the hydronium concentration. And here we plug this into the inverse log of the negative pH. And here is the value. Okay, so here's approximate pH values for some common solutions again. So you can see the hydronium concentration. So this is where it's saying if you have an integer, you can use that, but then it gets weird when you have a half, so don't do that. And then 4, you see it's the 4 here, 6 there, 7 there. That's what's saying which some of these are shortcuts that you can use. And then basic. Calculate the hydronium concentration in a dill pickle juice that has a pH of 3.22. Okay, so we're going to take the inverse log of the negative pH to determine the hydronium concentration. And this is 6.0 times 10 to the negative 4 molar. Okay, so now let's deal with the pOH. And when you do these, make sure you understand if you're working with pOH or pH, it can really mess up your answers. The pOH of a solution is defined as the negative logarithm of the hydroxide ion concentration. So if, remember, these are both equal when you multiply them to this number, which is Kw, and this is again showing you how it came up with these values. Here is the scales, so you can see what is most acidic and most basic, and here's the pOH, and here is the pH. Okay, so calculate the pH solution of a 6.9 times 10 to the negative 2 molar of sodium hydroxide. So we have a few things going on here. We need the pH, but pH is hydronium concentration, not hydroxide concentration, which is what we're dealing with. So we need to get the hydronium concentration in order to get the pH. So there's two options, two ways you can do this. This problem is going to show you two ways. The first way is to take the negative log of the hydroxide ions, and that will give you a pOH. But remember, a pOH is equal to a pH plus a pOH equals 14. So if you remember that, you can take this number, solve it, subtract it from 14, and it gives you, this number, it gives you the pH, which is 12.84. The second way to do it is use it with the Kw and get the hydronium concentration. So you plug this in, solve for the hydronium concentration, take that, the negative log of that, and it also gives you the pH. So there's two ways to do this. You should make sure you're comfortable with one of these ways. Okay, so calculate the hydronium concentration and the pH in. So let's just plug these in. So this is a strong acid. We plug it in and to the negative log, and it gives us 1.0 molar. And here we have a hydroxide ion. So again, we have hydroxide. We need the hydronium concentration. So we plug this in, get the hydronium concentration, do the negative log of that, and we have a pH of 13. So review, there are always some hydronium ions and hydroxide ions present in every aqueous solution, whether it's acidic, basic, or neutral. So basically what it's saying is that water autoionizes itself. We also have now come to understand the water ionization constant, which is Kw, and it is a constant. So that means if the concentrations of the hydronium or hydroxide ion change, they will change inversely. pH is another way to express the concentration, which is easier to understand. And getting the pH, you have to do the negative log of the hydroxide ion. pH is negative. If it's less than 7, it's acidic. If the pH is more than 7, it's basic. And if it's equal to 7, it's neutral. If the pH is known, then you can get the hydronium constant by using the inverse log of the negative pH. And if you need to know the pOH, then you do the negative log of the hydroxide concentration. And pOH and pH is equal to 14.